Okay, our final speaker of the session is Nai-Hui Chia, who's going to tell us about one-way permutations.
Okay. Hi, my name is Nai-Hui, and I'm from the Pennsylvania State University. And today I'm going to present our work on basing one-way permutations on NP-hard problems under quantum reductions. And this is a joint work with my advisor, Sean Holgram, and Fang Song from Portland State University. So one important question in cryptography is that how do people say a crypto system is computationally secure? And actually, if we want to say a system Y is computationally secure, then a very intuitive way to do that is that we have many experts that put lots of efforts on breaking system Y for a very long time, say after 50 years. And if we still cannot break the system Y, then we say, okay, Y is secure. But do we really need to wait for 50 years to prove that system Y is secure? Actually, you have a better way to do that, to wait for less years. Is that you can use some problems which is very hard. For example, SET. So SET has already been studied for more than 50 years. And SET is hard because it's NP-complete problem. And people believe that NP is not equal to P. So actually, we can use SET to show that problem Y is hard. So we can show that by finding a reduction from SET to Y. So what's the reduction is that you have an efficient algorithm A, and which have oracle access to an oracle of Y. So you can just view an oracle of Y as a black box, which you can ask questions to that black box, and that black box will give you answers of the corresponding questions. So you have an instance of SET to the algorithm A, and this algorithm will generate several questions to the oracle. And then he can use the answers and the input of the SET to come up with an answer whether the instance is in SET or not. And I want to point out that actually in this model, the algorithm A and questions and answers exchange between oracle and algorithm can be either classical or quantum. So if you can find such a reduction from SET to Y, it means that there's no efficient algorithm can break system Y unless NP is equal to P. Okay. So now let's consider a more specific system Y, which is called inverting one-way functions. So what is a one-way function? One-way functions are functions which are easy to compute but hard to invert. And it is a very fundamental crypto primitive. The existence of a one-way function implies you can do pseudo-random generators, digital signature scheme, message authentication codes, and so on. So now the question is that, can inverting a one-way function be as hard as solving a set? So actually, there are some no-go theorems for this question. So first result is by Bresa in 1996. He shows that if you can reduce SET to inverting a one-way permutation, permutation is a function which is one-to-one and onto, then it implies polynomial hierarchy collapse. And actually, complexity theorists don't believe pH will collapse. And there are other results related to one-way function, is that if you can find a reduction from SET to inverting one-way functions under certain constraint, then pH also collapse. And those constraints are like here, so the reduction are non-adaptive, which is by Akavia et al. In 2005. Or you consider functions which are prim-image verifiable. This is also done by Akavia et al., but there is an error in the proof, and Bogdanov et al. Improved the proof in 2015. Okay, so you can view this as no-go theorem for you cannot base one-way permutation or one-way functions on NP-complete problems because of these theorems. But for these reductions, they only consider classical reductions. So because we are quantum people, we are interested in quantum reductions, which means that we have our algorithm as quantum algorithm, and we have the message exchanged as quantum messages. So now the question becomes, suppose you have a hard problems, can you reduce these hard problems, like NP hard problems, to some computational tasks, like inverting one-way functions and so on? Okay, so here is our result. We show that if there exists a quantum reduction from SET to inverting one-way permutation under certain constraints, then CoAP is in another complexity class called QIP2. where our restriction is that the reductions are non-adaptive, which means that all the questions you ask to the oracle need to be independent. And the distribution of the questions you can ask are not far from the uniform distribution. And I also want to point out that this is unknown in the complexity theory. We don't know if CoMP is in QIP2 or not. So if you find a reduction satisfy the constraint, then it implies a very non-trivial consequence in the complexity theory. Okay, so let's just quickly review the theorem by Bressa in 1996, which is a very simple but beautiful proof. So he shows that if you can find reduction from set to inverting one-way permutation, it implies you can put CoMP in the N complexity class. And this implies the polynomial collapse. So actually what he did is that the goal is to construct a constant run protocol for the complement of set by using a reduction. So here is a reduction. And we need to know what is the M complexity class. So actually you can view it as a two-message protocol. You have a verifier and you have a prover. And the verifier wants to verify whether X is in L or not. And the prover tries to convince the verifier X is in L. And the protocol is like follows. The verifier first sends his random strings to the prover. And after getting a random string, the prover knows like all the behaviors of the verifier. Then he tries to generate a proof and use this proof to convince the author that X is in L. So here is the completeness and soundness condition of this protocol. So if X is in L, then there exists a prover can convince author the verifier. And if X is not in L, then no prover can convince author that X is in L. And this complexity class is in P space, and it contains NP and P. Okay, so this is what the proof looks like. So you have a reduction, and you want to construct an M protocol. So you make your verifier simulate the reduction, and you make an honest prover to simulate the oracle. So like the first message, the verifier sends his random string to the prover. And because prover gets a random string, he knows what questions the verifier wants to ask. So he just sends the questions and the answers to the question to the verifier. Of course, the malicious prover may send something different, but the verifier can verify whether the Y is the question he wants to ask and whether X is a pre-image of Y. If not, he just rejects. And if yes, he runs the reduction and decided whether to reject or accept according to the reduction. Okay, so this is a simple protocol, and you can prove it is correct easily. But can we use this protocol for quantum reductions? So the answer is no, because quantum reductions are more tricky. We have quantum messages exchanged between the oracle and the reduction. So we can view our quantum message as follows. So you have 3 registers, 1, 2, 3, and the first register is for the questions you want, the verifier want to ask. And the second register is for answers. And the third register is for some working qubits in the reduction. And you also have some coefficient here, and you can view it as the weight of the question Q. And here also the answers are in superposition, so you put your answers to the second register. And so why does the classical protocol fail? There are 2 observations. First, if you just try to simulate the reduction set to inverting one-way permutation, it only gives you quantum interactive protocol. And it is not an M protocol. And also, the prover can cheat by giving correct Q and the F inverse Q, but he can change the weight of CQ. It's like, okay, I can answer you correct, but I change your question. So now you have a different question, and you cannot verify whether the new question are the same as the old question you asked. So that's the 2 things prevent us from having a good protocol for it. So now we change our goal. We try to put a complement of set into QIP2. So what is QIP2? QIP2 is a quantum analog of M protocol. So you can view it as it is a 2 message, but these 2 messages are quantum messages. And you also have the same completeness and soundness condition. And the verifier sends quantum message to a proofer, and proofer send another quantum message back. And this complexity class is greater than the AM complexity, but it is in the P space. Okay. But actually, we don't know how to do it if we just have this one, so we add another constraint, which is that our reductions need to be uniform quantum reductions. So, which means that which means that your coefficient need to be all equivalent. And actually, we can extend this to like other distributions, but because due to the constraint of the time, I cannot show you this today. But yeah, we can deal with other distribution, not just uniform. Okay, so here we propose a protocol with trap. So which is that we have register M, which is, so the queries that verified sends to the prover is either a real query queue or a trap. And so the prover will respond different things according to the queries. So the main idea is that if a prover cheat, he has 1/2 probability to cheat on the trap state. And the verifier can catch him by verifying trap state. So we have two properties needed for this protocol. First, the prover cannot distinguish Q from T. So in his view, Q and T are totally the same. And second, if the prover cheats on T, the verifier should be efficiently verify that T is not the original T. So it means that prover try to do something on the state, and the verifier can know that. Okay, so here is our protocol. So we send the register M of Q or T uniformly at random. And then our Q is in this form. So it's like that we have the question, we have a register for the answers, we have our working qubits, and we copy another Q here in the fourth register. And our T looks totally the same, but the third register, we just put 0 here. And we send this to uniformly at random to prover, and on this prover will send ANS, which is that he just put the answers to a second register. And then the verifier does the following things to do that, is that in case of Q, he just run a reduction and accept if reduction accepts. And in case of T, he run a unitary which can map S, this state, back to the 0. This is easy because you can just erase this Q here, and you evaluate the one-way permutation to erase Q, and then you just do Hadamard to transform this one back to 0. Okay. So let's see why this protocol is correct. Here we just give the intuition why this protocol is correct. First, the prover doesn't know which state he gets. He gets this part of Q and T, but the reduced density matrix looks totally the same. So he cannot distinguish whether he gets Q or T. And this implies that if he tried to do something on this, except for the oracle, then he will either change S a lot or change A too small. If he changes S, the trap state too much, then by applying the unitary mapping S to 0, S point is far from 0, so the verifier can catch it. And if he changes A too little, then he cannot change the output of the reduction, so it fails to influence the verifier's decision. So in these two cases, the verifier can reject with high probability. Okay, so this protocol is correct. So here are some remarks about our theory. So it is that for this result, it is not as strong as pH collapse. However, it is a non-trivial consequence of the existence of quantum reductions. And second, we can extend this protocol to multiple non-adaptive queries. And we can deal with non-uniform distribution, which are not far from the uniform distribution by quantum resampling. Okay. So yeah, and here are some open questions. So first, which is a very intuitive question, is that can we deal with other distributions which are not close to uniform, or can we do for adaptive queries? And second, we should try to revisit other no-go theories for crypto primitives. There are some papers shows that it is impossible to reduce NP-complete problems to like PIR, FHE, or inverting one-way functions. But those works only consider classical reductions, and we should revisit them by consider quantum reductions. And can we have more evidence to show that CoMP is not in QIP2? And can we find other consequence which is stronger than CoMP is in QIP2? Like, can we put CoMP in QAM or QMA by having that quantum reductions? Or can we consider other consequence in the complex theory which is more unlikely? And also, it is very interesting to see if we can find other examples to show that quantum reductions are more powerful than classical reductions. There exists some problems which quantum reductions are more powerful than classical reduction, than existing quantum reductions. But now we cannot show that there exists a gap, which means that we cannot prove that classical reductions cannot do that. So I think it is an interesting question to ask this one. And last, generally we believe that quantum algorithm and crypto system lets computation secure. But you can think it as another way. Because quantum reduction is more powerful than classical reduction, maybe you can reduce some very hard problem, NP-complete problems to some crypto system, which is like proving some crypto system is even more secure. Okay, so that's the talk today. Yeah, I'd like to conclude my talk here. Yeah, thank you.